It's a great pleasure to be back here for an update on the story. I think if Bill Freeman is in the audience, Bill Freeman, so he says that he likes the story I tell, but it's a different story every time. So I'll try to convince you, Bill, that it's actually the same story. It's just evolving as we learn and understand more things. So before I start, actually, since this is about representations, let me state what I mean by representation, because the name means different things to different people, and see if there are objections to that. So at the most general level, to me, a representation is any function of the data that's useful for a task. Okay. Are there any objections to this? No, it's actually not a joke, because I have people object, because even this seemingly innocent definition carries some consequences. For instance, number one, if you tell me nothing about the task, there is nothing intelligent I can tell you about representations. I don't know what to say. So let me make this a little more concrete, because there's different types of data. The data you can use to construct a representation is past data, call it a training set if you wish. But I'm interested in accomplishing tasks in the future, and that will be based on data I haven't seen yet, so call this test data if you like. Okay? And of course, we need to agree on what we mean by useful, and we'll come to that in a second. And we want to be able to do so no matter what accidents affect future data, okay, that have nothing to do with the task. For instance, if I want to detect an object in a scene, detect a person, I want to be able to do so regardless of vantage point, illumination, partial occlusion, pose, clothing, you name it. Whereas if I want to navigate, then localization or pose is what I'm interested in, and instead reflectance property of the environment and other things are nuisances. Okay? Okay. Now, there is an easy solution of this problem. If you ask me what is the best possible function of the data that's useful for a task, I'll tell you the data. You cannot do better than that. That's data processing inequality. So we also want this function to be somehow easier to manage or easier to use than the data itself. Okay? So that's, in a little more color, what I mean by representation. Okay? So let me try to compress the statement by defining names. Actually, I don't need to define anything. These are very well and established concepts from classical statistical decision theory. So a function of the data is a statistic. We want to learn it. We want it to be sufficient, meaning as good as the data, can be no better. And we want it ideally to be invariant, if not insensitive to nuisance factor. And we want it to be minimal in some sense of complexity. It turns out it doesn't really matter what you choose as complexity, whether it's algorithmic complexity or information complexity. It generally relates to the size of the sigma algebra that you construct. So I'll come back to that. And ideally we want the components of this function to be independent. And this is measured by vector mutual independence or multi-information or total correlation. This quantity has different names. This is what people in deep learning often refer to informally as disentanglement. Okay? So you want, in one sentence, and by the way, as class of functions with respect to which we will try to solve this problem, we will use deep networks, not surprisingly, as a tool. And so what we want is basically any minimal sufficient invariant disentangled statistic. So this will be in three parts. So first, I will just instantiate and formalize the notions that I just stated in words. Okay? And this, again, has nothing to do with deep learning. Okay? We will arrive at a function that you want to minimize in a variational optimization problem to get an optimal representation. Then I will talk about what we actually do in deep learning, which has nothing to do with it. So what we do is we take empirical cross entropy, run SGD that doesn't know anything about sufficiency, invariance, disentanglement, doesn't know anything about that, and we get something. So I'll spend 10 minutes on this part of the talk, and there will be a dark rim around the slide so that you remember that we are in this part of the talk. And it would be surprising if doing this, which is minimizing an empirical loss using a first order fairly dumb algorithm, what we got was something that has anything to do with these desirable properties derived from first principles. Okay? And that's what is actually happening. So in the third part of the talk, I will establish a duality between a functional defined on the weights of a convnet, of a deep net, which are a statistic of the training set, what you saw in the past, and desirable properties of representations of future data, which you have not seen yet, in terms of sufficiency, minimality, invariance, and design time. So a representation is a function of the data that's useful for a task. So a function is, in this case, a stochastic function. So it's a random variable drawn by a posterior where the data x and the task y are also random variables. So a representation is any function from the posterior p of z given x. So it's a function of the data. And it has to be useful for a task, which means that it, the representation, must contain the same information about the task that the data does. Okay? So this is insufficient. You also want it to be minimum, meaning that among all the representations that are sufficient, you want one that knows as little as possible about the data, throws away as much of the data as possible. Okay? You want it to be invariant to nuisances, or if there are random variables that are independent of the task, then you would like the mutual information between that and the representation to be 0, or at least to be small, in which case I say insensitive as opposed to invariant. And then ideally you would like the components of this representation to be independent. So total correlation is also known as multi-information. It's a quantity that's 0 if the components are all independent. Let's focus for a second on two of these properties, minimality and sufficiency. So you can frame the problem of finding a representation as a variation constraint optimization problem. And you relax the inequality to with a Lagrangian, which is called the information bottleneck Lagrangian, and it looks like this. So given data x sampled from a certain probability, p, you are looking for a model q which minimizes the cross entropy, which is the cross entropy between p and q of the data given the representation, but that also tries to minimize the mutual information between the data and the representation. So this is the fidelity term. This is the complexity term. So this is all well known. Now, what might be interesting for you to notice is that this is actually the loss function that people use most commonly in deep learning. It's empirical cross entropy. But in deep learning, people don't use this added term. It's not there. Okay? So that's interesting, and we'll come back to that. Okay? So this formalizes the two of these properties, sufficiency and minimality. If I can solve this, I have a representation which is invariant, minimal and sufficient. Okay, this is all old news from the 90s. Okay, what about the other properties? Well, so you can prove very easily one result, which is that if you have a sufficient representation, then it is minimal if and only if it is invariant. Okay. One direction is very easy. The other, you have to prove that there always exist nuisances that achieve the bound. But essentially, what you're showing is that if you are able to minimize the information that the representation contains on the data while still being sufficient, then you also minimize the information that the representation contains about the nuisances. This is very intuitive. If you try to squeeze out as much as possible, you first throw out the stuff you don't care about that doesn't depend on the task, and you keep everything that depends on the task. Okay? Reasonable? Okay? So essentially what I'm saying is that you go for sufficiency, minimality, you get invariance for free, which is good to know. Of course, I haven't told you how we find these representations. That's going to come next. So the consequence of this is that so long as you have an architecture that you can train, you stand to benefit by inserting bottlenecks, either explicitly by adding this regularizer, that is typically not done, or by using architectural features like dropout or like pooling, or by stacking layers. And this is this is a sort of counterintuitive result, which says that if you have a representation that's sufficient, the more layers you stack, which means the more parameters you have, the more minimal you are. Just seems counterintuitive. You add more and more parameters and you become more and more minimal and therefore more and more invariant. But this is exactly what's happening. Because remember, you're measuring minimality not in terms of dimensionality, but in terms of information. Okay? Does it mean that the more layers, the merrier? We should just have infinite layers? No, because remember, this is given that it's sufficient. So long as you can train your network, which becomes more and more difficult, it's bigger, you stand to benefit by that. All I've done is formalize these notions that I stated in words at the beginning, and I came up with a cost functional, which is an information bottleneck Lagrangian, on the activation, which are a function of test data. You give me a test datum, I have a function, pass it through, I get z, okay? That z has these desirable properties. How do I get the function, okay? Well, I can only use past data, and so now we're in the second part of the talk. So far, there's nothing to do with deep learning, okay? Yes? Okay, so now I'm gonna make a 5-minute excursus into a completely different land that seemingly has nothing to do with it, okay? Okay, so in reality, what we do in practice, we take just one term of the loss function, the empirical cross entropy, but this is the empirical cross entropy not between test data and representation, but between the weights, which is what you're looking for, and the data, which is what you have. Now here you have to think of the data as a random variable, so your data set is a random variable, which is not too much of a stretch. And this is what people most often minimize when training deep networks. So you have W is in the millions or tens of millions or hundreds of millions these days. You run a gigantic high-dimensional convex optimization problem, and you use SGD. And this is a plot from Ben Recht. And part of the reason why people are puzzled is because they say, well, these deep networks, if you look at the bias variance trade-off, these deep networks should be over here because they have hundreds of millions of parameters, so they should overfit wildly, yet they don't. Why is that? Okay. So let's look at overfitting for a second, and let's say, what do we need to do to this loss to prevent overfitting, okay? So I'm going to write that term, the empirical cross entropy, this is what you minimize, as a sum of terms. I don't need to get into the details. The point is that these are all positive except for one. And this term, which you can easily maximize by storing the data set into the weights, therefore making this big, therefore making that small, is exactly what happens in overfitting, right? So theta is the true state of the world with respect to which this mutual information is computed, which is why you cannot compute this term. You don't know this term, okay? So, which is why we cannot just simply say, okay, let's just add this term to the loss function, and now we kill this, and now everything is positive and we don't overfit. That would be the solution of all of our problems in machine learning, except that computing this is not possible, okay? But what you can do is you can put an upper bound to this term that we can do, for instance, by computing the mutual information between the data set and the weights, regardless of what the state of the world is. So you upper bound that, okay? And so this is a loss function that if you can minimize, you don't incur in overfitting. But now this looks a lot like an information bottleneck, doesn't it? Now, it's not the information bottleneck that you usually hear about, okay? It's not the one that we talked about in the past or that Naftali Tishby talks about. This is a different use of the information bottleneck. It's information between the weights and the data set. Totally different business, okay? It's fascinating that it looks similar, and it would be even more fascinating if it had something to do with it. And it does because of the structure of the networks, not in general. Yes? Okay, so again, this is a new use of the information bottleneck. In any case, computing it, it's not easy, but it can be done these days with a few tricks. So now, I want to answer your question and say, people don't have that second term. They just have empirical cross entropy. So how is it that they minimize that term as well, implicitly? So you may have heard about this flat minima phenomenon, where you train a deep network, and it's very easy to minimize empirical cross entropy. Okay, you can make it 0, and then you try to see if it generalizes, and it doesn't. And sometimes it does, and you wonder what makes the difference. Well, if you look at the Hessian, at the eigenspectrum of the Hessian around a minimum that's a good minimum, most of the eigenvalues there are around 0. Then you have very, very few large ones, and you actually even have a very few small ones. But the point here is that people call these flat minima. It's a bit of a misnomer because there's no flat, but they're flat in many, many directions. Okay. Of the Hessian, of the loss function, or the empirical cross entropy around the minimum, around the next thing. Okay, so you're looking for flat minima, and people have known this for a while, since the 90s, in fact. Now, how do you actually find these flat minima? I will tell you in a second, but suppose you were lucky, your stochastic linear descent, without knowing anything about information or anything like that, converge to a flat minimum. Then what happens? So this is the nuclear norm of that Hessian. So if you're flat, this thing is small. This is the L2 norm of the weights. This is called weight decay. It's a regularizer. You have a constant here. So if you make this small, you make this term small in the information model. So if your SGD was successful, you have already minimized this term, in addition to minimize cross entropy, which means successful training. Okay, so that answers your question. Okay, so without knowing it, if you are lucky and converge to the flat minimum, this happens. Of course, the converse is not true. So there's a paper say flat minima, so sharp minima can generalize. Of course, this is an inequality. If they're flat, they generalize, but they can generalize without being flat. Not only, but this quantity is invariant to reparameterization of W. This is not. So this is really the quantity that you should pay attention to, the information in the weights. And by the way, Jeff Hinton in '93 had a paper that says we should minimize the information in the weights in these networks for compression purposes. Of course, in '93, we have no idea how to actually do that, but that's actually the right quantity. It's pretty amazing. Okay? So if you have an algorithm that find flat minima, then you're in business. And I'll come back to say how you do that. So let me answer the question that was asked earlier. So what beta do you choose? So let me show you the following plot. So you've seen this paper titled Rethinking Generalization. Deep networks require rethinking generalization. So Ben Recht and coworkers take a bunch of random labels, train a deep network, and show, look, the network can train random labels. Okay. So what you show here is exactly the same experiment. Every point here is the residual of a conv net taken to convergence as a function of the size of the data set and beta, the amount of information you allow the weights to have. Okay? So given you have enough capacity, you can achieve high accuracy over fit on any random labels. Of course, the bigger the data set, the more labels you need, and there is a very sharp phase transition from underfitting to overfitting with pretty much nothing in between, exactly at this predicted boundary, which is exactly the boundary that corresponds to beta is equal to 1. So the theory predicts this phase transition and predicts exactly the spot where it will happen. Okay? Predicts, given a particular network, the size and the information you need to allow. For instance, if you take MNIST and take 0% random labels, and then you add more and more random labels up to all of them, then you need to, in order to overfit, you need to increase the amount of information by 2.7 nuts, which is exactly the amount of information you need to store the data set. So you can predict quantitatively. Okay? And if you use the information in the weights as a measure of complexity, not the number, then this follows the bias variance plot exactly. Okay, so there's no need to rethink it. Okay, so this is what we do today. So we take SGD, okay, we take cross entropy, we run SGD, and we try to find flat minima. And if we do so, then we can generalize. I still have told you nothing about how this connects to the desirable property representations. But let me open a 5-minute break and tell you how we actually find flat minima, because this is a different chapter. And this is work of Pratik Chowdhury, who some of you might know, because he was here before he came to UCLA. So this is the cross-entropy loss that people minimize. And they minimize it with stochastic gradient descent, where you take an initial condition and you add a perturbation, which is an approximation of the gradient with respect to some learning rate. And there's a little bit of black magic in how to choose those. Okay? So Pratik was looking for ways of modifying stochastic gradient descent to seek for flat minima. And it turns out there are some ideas in statistical physics that people have used. And I'm going to present it to you in a way that doesn't do justice to all the statistical physics that is behind it, but the idea is very, very simple. So let me just explain the idea. If you're trying to minimize a loss, highly complex, non-convex, high-dimensional problem, what you do is you amplify, so you exponentiate the loss, smooth it with a Gaussian, and then bring it back with a log. Okay, seems like a hack. This actually has a name. It's called local entropy. Okay. And statistical physicists have been studied that. Think of it as a relaxation, where as sigma goes to 0, you get the minimum of the original function, and for large sigma, you get something. Okay?
What is G?
G is a Gaussian kernel with a sigma standard deviation, spherical kernel. So I'm going to take local entropy, and I'm going to write it as a function of x, now the general unknown. I apologize for the confusion. Now, from the next few slides, x is going to be not the data, but the unknowns. I'm just switching the notation for you, so the audience becomes notation invariant. So you learn the concepts, not the symbols. Actually, this is because so that if I go and read the papers, because this is standard notation in this area, you recognize it. So this is what the expression that you will find for local entropy. Okay. So let me spend 5 minutes telling you how to minimize local entropy. Here it is. If you compute the gradient, it looks very, very simple. The gradient subtracts from the current iterate a local average, which you can compute as an expectation over a local Gibbs measure, which you can compute or approximate using Langevin dynamics. It's just a form of Markov chain Monte Carlo. Okay? So very easy to compute. Okay? This parameter, the sigma, which I now change to gamma, again, to keep you awake, is called the scoping parameters because it sort of determines the scope of sampling of the Markov chain Monte Carlo, how you sample around the current local iterate. Okay? And the algorithm boils down to two loops, two nested SGD. The outer loop is just standard SGD, and the inner loop is this local entropy computation. Okay? Now, this is the expression. And one thing to notice is that this looks a lot like versions of distributed, in fact, the generalization of the most popular algorithms for distributed training, distributed SGD. For instance, elastic SGD, where each worker, instead of computing a local average, computes local entropy. So each worker does a lot more work, and then they just communicate the mean. So there is a distributed version of this algorithm, which is called Parley, that achieves state-of-the-art results today. Okay. So here's some data. So this is CFAR 10 and CFAR 100. So black is standard SGD. Red is entropy SGD. So here, each point is one epoch. So in terms of number of iteration, this is a tiny, tiny fraction of SGD. But of course, each iteration costs more. So what I'm plotting here is actual wall time that takes into account the additional work. But what you can see here is that not only you converge faster, but you converge actually to a lower risk than SGD will ever get. Okay. If you take SGD, you can write it as a discrete equivalent of a stochastic differential equation that looks like this. Okay. So U here is the solution. So this is local entropy, okay, not just a standard SGD. So U is the original function. So F is the original function trying to minimize. U is local entropy. You run this PDE backwards, and that's local entropy. Okay, so you're trying to solve the stochastic differential equation. There is actually a stochastic optimal control problem that corresponds to this. So the cost to go here is, so that the gradient of local entropy is cost to go. Okay, and now that you have a PDE, you can actually play with a regularizer and say, you know, the way it's framed is a viscous PDE. There is a viscous term. You can also remove the viscous term, have a non-viscous PDE. And the non-viscous PDE has actually a very simple solution, which has a proximal iteration. And this relates to the Moreau envelope or Inf convolution and can be solved with a hot flux formula. Okay, so there is a very, very simple iterate for the solution. There is a Fokker-Planck equation, and the Fokker-Planck is linear, and you can say nice things about the distribution of the weights at solution. One thing which is remarkable and almost magic, and I cannot say I understand this, but PDE people are very excited about this. So if this black thing is the original cost function you're trying to minimize, this is a 1D example, okay? This is the distribution of solutions you find with standard SGD, okay? So it's the distribution plotted as grayscale. If you do, for instance, a diffusion process like a heat equation, you get the red curve. And what diffusion does in general, it moves both the location of the extrema as well as the value of the extrema, as well as the topology, because extrema merge and split and so on and so forth. Okay? What this type of PDE does is you can prove that it leaves the minima exactly where they are in both value and location, and kills all the other extrema. The maxima turn into kinks. In the first part, I said we want representation which are functions of future data, test data, that are sufficient, invariant, disentangled, and minimum. Here I said we are looking at function of past data, okay, and we want it to generalize, and so we want flat minimum, so that the information, the weights contained about the data set is small. There's, in theory, nothing that connects the two. And in general, there is nothing that connects the two. The question is there something special in deep networks that does connect the two? And that's exactly what happens. Okay? So remember, this is what gets minimized when you find flat minima. Flat minima, you find solutions where the information in the weights, the information that the weights contain about the data set is minimized. Okay? On the other hand, you would like to say something about the information that the representation function of future data contains about the data, because this tells you about minimality, and that tells you about invariance. And then, coming to Paulina's question, you also would like to minimize total correlation because you want disentanglement. So these two things lead into a completely different world. Function of past data, function of future data. Okay? There's no connection between the two. Okay, the question is there a connection for deep networks? And the answer is that there is. So there is a function which is strictly increasing so that the information in the weight bounds the sum of the minimality, hence invariance, of the activations and total correlation. And for one layer, this is a tight bound. Okay? For multiple layers, cannot be tight because you don't know where information is lost in the layers, but it is nevertheless, there is a more complicated bound. Okay, so this is really, it's not an optimization result, it's a deep learning result. It's only specific to deep networks. So if you do your job well in SGD, and SGD doesn't know anything about minimality, invariance, and so on and so forth, you manage to minimize this. Okay, so that's basically what, the gist of it is that you should be looking, as you're training your deep networks, for ways to minimize the information, the weights contained about the data. And there's multiple ways of doing that. One of them is to explicitly add this term as a regularizer, okay, which nobody except us do, but it can be done. Or you can rely on SGD or versions of SGD to implicitly minimize this. And this is what is happening. Or you can rely on architectural characteristics to force the minimization of this information. Yes? So there are these three ways in deep learning of minimizing this information. But the point is that this is really the important thing to keep in mind when you're training deep learning. Now, this is written in terms of mutual information, which has some problems because you say, well, I have to assume a posterior of the weight given the data set. The data set is treated as a random variable. That's a bit strange. I'm giving one data set, not a distribution. So that's all valid. You can fix it with some technicalities, but you can also show that you can derive exactly the same bound using path bias framework without using mutual information at all. And you can also use it with Kullback-Leibler, so you're not confined to finite sets or finite dimensional space. Okay, so that's essentially the gist of it. So what I showed you is work that I started back in 2005, in fact, that I've talked about in this venue before, which is we want representation which are a function of the data that's useful for the task. We want it to be sufficient. We don't want it to throw away information. One of my mentors, Don Snyder, said that his mother always told him to never throw away information. We want them to be minimal, so we don't squander. We want them to be invariant, so we don't worry about things that we don't care about. And we want it to be easy to work with, so disentangle and so on. Because this is actually one of the cases where you want to throw away as much as possible, so long as you maintain sufficiency for the task, which depends on the task. If your task is compression, you want to preserve every pixel. You have to keep a lot of stuff. If your task is telling apples from oranges, you might do with 1 bit, and then you throw away almost everything. But the point is that forgetting about the task helps you in the future, and I'll leave you with that thought. And I'll put the faces of the main engines behind this, Alessandro Achille and Pratik Chaudhary. Alessandro is working on the modeling side and Pratik on the optimization side. So you and then Paulina, and then again. Thank you.